Hi friends, we have already studied operational amplifier as voltage amplifier. In this lecture, we will study general types of amplifier and their non-idealities. We will also study that how they can be made ideal. What should be the values of non-ideality so that to make them ideal amplifiers. In general amplifier, we will study four types of amplifiers. We have studied voltage amplifier in which voltage input is voltage and output is also voltage. If we talk about in terms of input and output, input can be voltage, output can also be voltage, or input can be voltage and current. Similarly, output may also be voltage and current. So we have two combination in input and two combination in output. So in total we may have four combinations. In amplifier, what we may have, we have input and output. For both input and output, we may have voltage here, we may have current here. Voltage and current, here also we may have voltage and current. If both input and outputs are voltage, we will say it as voltage amplifier. Voltage amplifier. Okay. If both input and outputs are current, okay, we'll say it current amplifier. If input is current and output is voltage, then this will be called, okay, the unit of output versus input will be a resistance. So this will be called trans-resistance amplifier. Trans-resistance amplifier. And if input is voltage and you are taking output as current, this will give you current divided by output divided by input, means current divided by output. Its unit will be conductance. So this will be called transconductance amplifier. Okay, so here we will study these four types of amplifiers. Out of these four types of amplifiers, we normally study voltage amplifier in op-amp, but we also need to have little bit idea about these amplifiers. Okay, when we will study feedback or effect of feedback, we have to study four types of feedback connections. There are four types of feedback connections: voltage series, voltage shunt, then current series, and current shunt. In all these four types of feedback connection, we will see the effect on voltage gain, input impedance and output impedance. So to see the effect of these feedback on the overall system gain, overall input impedance, overall output impedance, we must have idea about ideal current amplifier, ideal trans-resistance and transconductance amplifier, and what is the meaning of, what could be the non-idealities and what is the meaning of ideality. Okay, so question may be asked on this amplifier, and even if question is not asked, the use of these concepts will be in feedback. So we will study all four types of amplifier. Okay, so let us first start with voltage amplifier. In operational amplifier, when it works as voltage amplifier, what is the condition for operational amplifier to be ideal? In case of operational amplifier, what we say, its gain must tend to infinity, its input impedance, this must tend to infinity, and output impedance, this must tend to 0. So this is the case of ideal operational amplifier. In case of general voltage amplifier, if we talk about ideal voltage amplifier, the gain not necessarily need to be infinity. It may have some finite gain, okay, but its input impedance must tend to infinity and output impedance must tend to 0. So this is case of ideal general voltage amplifier. General voltage amplifier. Okay. Now with the help of example, we will see that if input impedance is not infinite or output impedance is not 0, then what will be the effect and why it will be called non-ideal. Okay. So let us first make a circuit diagram or a model of general voltage amplifier. Let's say we have a voltage amplifier with gain A and which is not ideal, so it will have some finite input impedance and finite output impedance. Okay, so what will be the model of general voltage amplifier? I will represent it with a box. Let's say this is a voltage amplifier circuit. We will connect an input here. There will be some input to voltage amplifier and there will be some output. This is output terminal of voltage amplifier and this is input terminal. Whatever is the voltage is being input to this amplifier, I will represent that voltage with Vi, as I represented in case of op-amp. The input to this amplifier will be Vi, and there will be one more input voltage, that will be system input voltage or source input voltage. Now if you are required to amplify some voltage, as we have voltage amplifier, so input will be voltage and output will also be taken as voltage. We may have a source voltage, the voltage which is to be amplified. Okay, talking about this amplifier, it has a finite input impedance. What does it mean? It has Zi input impedance. It means if the input to the amplifier is Vi, it will take an input current of Vi divided by Zi. Zi will be input voltage to the amplifier. This may not necessarily be equal to the source input voltage. Okay, there may be some resistance here. Okay, Zi will be in the voltage which is being input to amplifier divided by current taken by the amplifier. So where this Zi to be connected in the model of amplifier, we will connect Zi at the input terminal. Let's say this is, instead of Zi, let's say this is resistance. In general, this may be combination of resistance, inductance or capacitance, but for simplicity I am taking it as resistance only. Now if you connect a resistance here, you will always get, if input current is II, you will always get Vi divided by II equal to Ri. For modeling this voltage amplifier, Ri is connected here. Okay, it seems that we have connected Ri parallel to the source voltage. It seems that. Now why I have not connected Ri here? Let's say to this voltage amplifier, we are required to model Ri. We have a question where we should connect Zi. Now let's say I am connecting Zi here. You have to connect Ri such that the whole amplifier input voltage must drop across the input impedance. Okay, so if this is input voltage to the amplifier, this must drop across the input impedance of the amplifier. Okay, now we have to model output impedance. The question is, as name suggests, it has to be connected in output. Okay, so there are there are two possibilities. We can connect output impedance here. We have this output terminal. There are two possibilities. We may connect output impedance here, or in the second case, output impedance can be connected here also. So which will be correct? Okay, or before modeling output impedance, let us first talk about voltage gain. What is the meaning of voltage gain? Output voltage will be equal to voltage gain. Output of the amplifier will be gain into input of the amplifier. Okay, so let's say this is output voltage of the amplifier. So this will be equal to, here we will connect a voltage dependent voltage source. This is output voltage, and what will be gain here? This voltage will be A into V naught. So what we have here, we have a voltage dependent voltage source, A into Vi, if we have voltage Vi here. Okay, now the question is Z0 in the output terminal, whether Z0 should be connected in parallel to the output terminal, or it should be connected to the series of output terminal, in the series of output terminal. Here we have A into Vi. Okay, so we can find out the answer with the help of definition of output impedance. What is the definition of output impedance, or how we calculate output impedance? To calculate output impedance, we first set input voltage Vi to 0. Then we connect a voltage source in the output. Let's say we connect V0 voltage in the output. Then we find output voltage divided by current drawn from the output voltage. So if you will set Vi equal to 0, suppose you are setting Vi equal to 0, if Vi is 0, this voltage source will be 0, and if this voltage is 0, this will be shorted. Here also this will be shorted. Okay, now what we need to do, we will connect a voltage source in the output terminal, and now we will try to find out what current is being drawn from this source. Now if this Z0 is connected in parallel, what current it will draw? The current will be, or let's say this is the current. Since this is short, an infinite amount of current will be drawn from this source. Or after connecting this voltage source, we have to find out the impedance seen from this terminal. If you will see impedance from this terminal, this is Z0 parallel 0. Infinite amount of current is drawn, so the output impedance will be V0 divided by I0, and I0 is tending to infinity, so you will get it as 0. Okay, and here this is shorted, so current will be V0 divided by Z0, and from here you will get V0 divided by I0 equal to Z0. So we have already defined the output impedance is Z0. Okay, so now after you already know the value of Z0, here you have connected Z0 in parallel to the output terminal, and you got output impedance as 0, which is incorrect, and here you got the correct result. So the output impedance will be connected in series in case of voltage amplifier. Similarly, I can show that if at the output terminal, what we are taking here, in the output we are taking voltage. If at the output terminal we are taking current as output, if you are taking current as output, okay, I will do this later. First I will complete voltage amplifier. Okay, so we have already modeled the open loop gain A. This is A into this voltage will be A into Vi, A into Vi, okay, and output impedance will be connected in series with the output terminal. This is a non-ideal amplifier having finite Z0 and finite Zi. Okay, so this is final output terminal. Okay, so let us put some numerical value. Let's say we have a voltage amplifier with input impedance equal to 10 kilo ohm, output impedance equal to 100 ohm, and voltage gain equal to 50. So how will we model it? Representing a voltage amplifier with resistance or with a circuit diagram will be called modeling of a volt amplifier. Okay, so its input impedance is 10 kilo ohm, this is 10k. Okay, this will be, if this is input to this voltage amplifier, this voltage will be 50 into V input. Okay, okay, now you have a source voltage and you want to amplify this voltage. Let's say this is of 1 volt. This is of 1 volt, and every source have, what is the modeling of source? If it is an ideal source, this will be modeled as a voltage source, simply V. But if it is a non-ideal voltage source, how will we model it? It will have some internal resistance, and that resistance is modeled in series with this voltage source. So this is modeling of a non-ideal voltage source. So let's say you have a non-ideal voltage source and it has internal resistance as, let's say this is 2.5 kilo ohm. This resistance seems to be very large for a voltage source. Let's say this is 100 ohm, and the input impedance is, it should be high, but for just to show the effect of non-ideality, I'm taking as a low value. This is all, let's say this is 400 ohm. Okay, now if you want to calculate the output voltage, the formula for output voltage is gain into input to the amplifier, not the input voltage. This is system input voltage, Vn or Vs. Vs. The overall gain will be, let's say I'm representing it with AV. This will be the output voltage divided by source voltage. Okay, and since we have an amplifier, the amplifier output voltage will be gain into the input voltage to amplifier. What I'm trying to convey is, you have connected a voltage source of 1 volt, but it is not necessary that the whole 1 volt voltage will appear across the terminal of this amplifier. Okay, now if you have connected a 1 volt, what will happen? Let's say this is 10 volt. There will be a current. If there is some current, what is the input voltage to amplifier? The input voltage will be, from voltage division, 10 volt into 400 divided by 100 plus 400. This will be 8 volt. So we'll say V input equal to 8 volt. Okay, so what will be the output voltage? Let's say we are first calculating open circuit output voltage. So what will be the voltage here? First we will calculate this output voltage. The output voltage of the amplifier, this will be 50 into 8, 400 volt. Okay, you have connected a 10 volt and the gain of amplifier is 50. So what voltage you were expecting? The input voltage you have connected 10 volt and gain is 50. You were expecting 500 volt as open circuit output voltage, but what actually you are getting? You are getting 400 volt. So why you are getting 400 volt? Okay, let us not answer this. Let us first answer or first check if this impedance was very high. Let's say this impedance is 10 kilo ohm, or let's say this, okay, this impedance is 10 kilo ohm. Now what will be the value of Vi? 10 kilo ohm, 10,000 divided by 10,000 plus 400. So here Vi will be 100 divided by 100, 4, 10 into 100 divided by 104. If you will calculate it, you will get approximately you will get 9.6 volt. Let us calculate it. 100 divided by 104. Okay, you will get approximately 9.61. Now if you will calculate output voltage, output is 50 into 9.61. This will be 480 volt. The expected voltage is 500. When you put Ri equal to 400 ohm, the output voltage was 400 volt. When Ri is 10 kilo ohm, output is 480. So what you observe here, if you increase input impedance, you are getting a result which is closer to the expected result. Now if you will connect an infinite, let's say its input impedance is infinite, so there will be no current. If there is no current here, there will be no voltage drop across the non-ideality of voltage source. So if there is no voltage drop, whatever voltage you will connect here, the same voltage will appear across the input of voltage amplifier. This is 10 volt. Now if this is 10 volt, the 10 volt will be multiplied with 50. So now you will get 500 volt. Okay. So what is the reason of getting a reduced output voltage? If you have a low input impedance, a large value of current will flow, and due to that current, a significant amount of voltage will be dropped across the non-ideality of source. So if you are connecting 10 volt, if this input impedance is not infinite, there will be a flow of current, so you will not get a 10 volt across the input of amplifier. So you will get reduced input voltage, you will get reduced output voltage. Okay, so this was the effect of a finite input impedance. Now in the same example, we will try to see the effect of output impedance. Okay, till now we were calculating open circuit output voltage. So whatever voltage will be here, since there is no current here, so there will be no voltage drop across this 100 ohm. So the whatever voltage is here, the same voltage will be equal to output voltage. Okay, so this was the effect of a finite input impedance. Now we will set it as infinite. We will make this amplifier ideal in terms of input impedance, but we will keep this non-ideality here, and now we will connect a load resistance here. Let us take the same numerical values. We have a source of 10 volt. It has internal resistance of, this was 100 ohm. let's say input impedance of this amplifier is infinite. Okay, so no current can flow here, that's why I'm leaving it as open circuited. This voltage will be input to the amplifier. The open loop gain is 50, so here we'll have 50 into Vi, and it has an output impedance of 100 ohm. Okay, so you have to amplify a voltage. So what you will do after amplifying this voltage, you will certainly give the amplified voltage to a load. So let's say in load we have a resistance of, let's say we have a resistance of 100 ohm. Okay, so you have connected a 10 volt, the gain of amplifier is 50. So what voltage you will expect across the load? The load voltage you will expect 50 into 10, a voltage of 500 volt you are expecting across load resistance. Okay, now if we calculate it, we have 10 volt here, input impedance is infinite, so Vi will be 10 volt. If Vi is 10 volt, this voltage will be, this is op-amp output voltage. Okay, and this voltage is load output voltage. Okay, so this voltage is 500 volt. Now what will be VLD? Again, if we apply voltage division, VLD will be, this will act as source voltage 500 volt into 100 divided by 100 plus 100, you will get 250 volt. Okay, in the previous case this was open circuited, so if this is open circuited, no current can flow here. If no current will flow here, there is no voltage drop. But if we have a load resistance, certainly there will be some current in the load, and the load current will flow through the output impedance of voltage amplifier. So there will be a voltage drop in the output impedance. Now if you want this voltage as your expected voltage, you want all this voltage to drop across the load resistance, but it is connected, so there will be some current. If there is some current and still you want the total voltage to drop across this resistance only, this resistance has to be 0. Okay, so what we have observed here, to get the expected result, Zi should be infinity and Z0 should tend to 0. Now suppose we want the effect of input impedance and output impedance in one expression only, considering all the non-idealities. This is amplifier, we have a voltage source with Rs, its non-ideality, Zi as input impedance, Z0 is output impedance, and in the load we have connected a resistance RL. If you have connected a voltage source Vs, in the output the expected result is A into Vs. This is expected result. If this voltage is Vi, this voltage will be A into Vi. So first we will calculate Vi, then this voltage, and then the final output voltage VLD. So what will be this drop, this voltage? Vi will be Vs into Zi divided by Rs plus Zi. Okay, and now VLD will be this voltage. This voltage is nothing but A into Vi. A Vs into Zi divided by Rs plus Zi, this voltage, into, this will act as source voltage. Now we will apply voltage division. This will be RL divided by RL plus Z0. And suppose this is expected voltage. So what is actual load voltage divided by expected voltage? This will be Zi divided by Rs plus Zi into RL divided by RL plus Z0. This quantity is also less than 1 and this is also less than 1. So overall you will get this quantity, you will get the reduced output voltage. This is the effect of input impedance and this is corresponding to output impedance. If you put Z tends to infinity, this quantity will give you 1. If you put Z0 tends to 0, this will also give you 1. So in that case you will get no reduction. Okay, so this was about voltage amplifier. Next we will study current amplifier. In case of current amplifier, both input and output will be current. We will have an amplifier in which there will be a current source Is, and in the output we will expect an amplified current. Let's say this is I0 and this is current amplifier. Let's say this is a finite input impedance Zi, finite output impedance Z0, and current amplification A. A is nothing but output current of amplifier divided by input current of amplifier. Now we have to connect Zi and Z0 in proper way according to definition of input impedance and output impedance. So what is Zi? Zi is nothing but the voltage across amplifier divided by current taken by it. So Zi will always be connected across the input such that all the voltage appear across Zi, and this will be the input current to the amplifier. If this is input current, we will have a current dependent current source. Here we will have current dependent current source, and this will be gain into input current. Okay, now the question is where to connect Z0. Obviously Z0 will be connected in output, but whether it should be connected in series with the output or in parallel with the output. Okay, so to answer it, let us first connect it in series. Let's say input current is II, here we will have A into II, and I am connecting output impedance here. Now from the definition of output impedance, how we will calculate it? We will first make input 0. Okay, so input 0 means what is at input? At input we have current, and what is the meaning of making current 0? Leave it open circuited. Okay, if you don't apply any source, II will be 0. If II is 0, this current is 0, and making this current is 0, what does it mean? Will it be open circuited or short circuited? If this current is 0, you have to ensure that no current flows here, so you have to make it open circuited. Remember, in previous case we had a voltage source here, so making 0 a voltage source will mean that you have to short circuit it. Now but if you have a current source, if you have to make it 0, it means you have to open circuit it. So if II is 0, this is 0, now you will open circuit it. Okay. So to calculate Z0, what we have done, input is 0. We made input 0, then we will calculate a voltage source. Then we will connect a voltage source. And if this current is I0, V0 by I0 will give you Z0. Now if Z0 is connected here, what will be the current? Since this is open circuited, I0 will be 0. So what will be the value of V0 by I0? V0 by 0. This will give you infinite. But you should get output impedance as Z0 because it is given. Now if it is connected in parallel to the output terminal, in the same way we connected no input, this was 0, open circuited, so no current will flow here. But if it is connected in parallel, I0 will be now V0 by Z0, or V0 by I0 will be Z0. So in this case we are getting correct result. So in case of current amplifier, or if we have output as current, we need to connect the output impedance in parallel. I should model this Z0 inside the box only, because inside the box we have amplifier and Z0 is part of amplifier only. So this is Z0. Okay, and this will be the final output current. Outside the box we will have final output current. Okay, so we have Zi, gain and Z0. We have complete model of a current amplifier. This will be circuit model of a current amplifier. Now we have to modify the value of Zi and Z0 in order to get an ideal current amplifier. What we did in case of voltage amplifier, we connected a voltage source, but in case of current amplifier we have to connect a current source. So let us, we have a current source Is. If it is an ideal current source, there will be no resistance, but if it is non-ideal, there will be some resistance. And in case of non-ideal current source, the non-ideal resistance will be connected in parallel. This will be Rs. Now this non-ideal source will be connected to the current amplifier. In case of non-ideal voltage source, we have Vs here, and the non-ideal resistance is connected in series. In case of, if you want to convert this in a non-ideal current source, you will just take the source transformation. This is a voltage source, you will do the source transformation of this, so you will get non-ideal current source. Okay, so what do you want? If the source current is Is, in the output what you will expect? You will expect a current of A into Is. Let's say in the output we have a resistance here, load resistance. Okay, so first talking about input impedance. If you want the expected result, so what should be the current here? The current should be here A into Is. Or first talk about output side. Whatever is the current here, this current is going to be divided into the output impedance and the load resistance. Now if you want, in ideal case, what you will want, all the current which is being generated or which is flowing from the amplifier, all the current should go to the load. There should not be any current in the output impedance. So for this, what should be the output impedance? If this impedance tends to infinity, there will be no current, and all the current from this amplifier will go to the load. So if current is A into Is here, all this current will flow through the load. So in case of current amplifier, you want output impedance as infinity. Okay. Now you want Is current. So here current should be Is, A into Is. So I must be equal to Is. This current must be equal to Is. Means what you want, whatever is the current supplied by source, all that current must enter to the amplifier. But what you are seeing, observing here, this current is going to be divided into the source resistance and the input impedance or input resistance. Okay, we are not going to change it, this will be fixed. You can change it. Now if you want all this current to flow from here, this is finite resistance, what should be this value? I will be, from current division, this will be Is into Rs divided by Zi into plus Rs. So if you want this current to be Is, okay, Zi must be 0. If you will short circuit it, certainly all the current will flow through short circuit. Okay, I hope I was little bit fast here, but since we have done in case of voltage amplifier, I gave much time there and the case is similar, so I hope you understood it. So in case of current amplifier, Zi must tend to 0 in order to get all the current from the source into the amplifier, and Z0 must be infinity such that all the current amplifier should go to load. In case of transresistance amplifier, input will be current and output will be voltage. So we will have an amplifier. Here we will have non-ideal current source. We already know how will be the non-ideal current source, with some internal resistance Rs. The input impedance Zi will be connected such that all the voltage drop across this and current, all the current to this amplifier flow through the input impedance. Okay, what we will have here, we will have a dependent source. And how will be this dependent source? The input will be, input is current, so the input of to the amplifier is, let's say, II, and output has to be voltage. So this will be a voltage source, but it will depend on current, so this will be a current dependent voltage source. And in the output, since we have a voltage, so how output impedance will be connected? In case of voltage amplifier, what we observed, in the output we had voltage, and if we have voltage in the output impedance has to be connected in series with output terminal. This has to be connected in series with the output terminal. And in case of, if we have current here, this output impedance will be connected in parallel to the output terminal. Let's say we connect a load resistance, and this will be our final output voltage. Okay, so to make it ideal, now you'd have got much idea about it. To make an amplifier ideal, what you want, all the source current or all the source voltage must drop across the amplifier, or whatever, and after that whatever voltage and current is being produced by the amplifier must go, all this voltage or current must go to the load to make it ideal. So let's say we have IS current here and you want all this current to flow here. So what should be the value of Zi? Zi should be, this should tend to 0. If you will short it, all the current will flow through short circuit and II will be IS. Now you have a voltage source here and you want all this voltage to drop here. Okay, so there should not be any drop across this Z0. So what should be the value of Z0? Z0 should tend to 0. Similarly, for transconductance amplifier, in case of transconductance amplifier, at input we have voltage and at output we have current. So we'll have a non-ideal voltage source with internal resistance Rs connected in series. Zi will be connected in series. This will be Vi, input voltage to amplifier, and this is Zi. The output has to be a current, so we will connect a current source here. And how will be this current source? Since this depends upon the voltage, so this current source will be a voltage dependent current source. The amount of current will be A into Vi. In this case, the gain will be, in case of trans resistance amplifier, gain will be voltage divided by current, and in this case gain will be current divided by voltage. It will give you the unit of conductance. Now in the output you have a current source, so how will the output impedance be connected? This output impedance will be connected in parallel. Okay. And here we will have output current, final load current. Okay. So again, for ideality, all the source voltage must drop across the amplifier. Okay. If you want all the voltage source to appear here only, the drop here should be 0. So to make this voltage drop 0, current should be 0. And to make this current 0, the impedance should be infinite. So input impedance must be infinite. If we talk about output impedance, whatever current is produced by this amplifier, all this current should flow through the load resistance. Okay, this is finite and fixed. You don't want any current to flow here. Okay, so this impedance also should be infinite. So first we studied the case of voltage amplifier. In case of voltage amplifier, input impedance must be infinite and output impedance must be 0. In case of current amplifier, the input is current and you want all the current to flow to enter into the amplifier. Okay, so amplifier input impedance must be 0. And since it is a current amplifier, it will produce a current in the output. And you want all the current to flow from load. There should be no current in the output. So output impedance must be infinite. Okay. In case of trans resistance amplifier, the input is current and you want all the input current to flow through amplifier. So there should be no current in the internal resistance of current source. At input you have a current source and you don't want any current in the internal resistance. You want all the current to flow from the impedance of amplifier. So this impedance should be short. So input impedance must tend to 0, and in the output you will have voltage in the output you will have a voltage source, and you want all the induced voltage or produced voltage to drop across load resistance. You don't want any voltage across this output impedance, so output impedance must be 0. And in case of transconductance, the case will be reverse of transresistance. So Z input must be infinity and Z output must be infinity. If voltage is an input, then what should be the input impedance? If voltage is an input, the input impedance should be infinity. Okay, and if current is an input, the input impedance must be 0. Okay, if voltage is an output, the output impedance must be, in the box I am writing in impedance, and if current is an output, the output impedance must be infinity. Okay, with the help of this table you can remember all the 4 cases, but in each case you have to remember what is input and what is output. Let's say for this case, what is input? Input is voltage. So if input is voltage, so input impedance must be infinite. That input must be infinite. In transconductance, what is output? Output is current. Output is current. So output impedance must be infinite. Okay. So if you remember this table, you can easily remember what impedance should be infinite and which impedance should be 0. Input, if voltage is in input, impedance must be infinity. If voltage is in output, output impedance must be 0. Okay, so this was the the 4 kinds of ideal amplifier. In the next lecture we will study the effect of feedback. To see the effect of feedback, we will have a non-ideal amplifier, and in the feedback we will connect any of these 4 amplifiers. That will depend upon what is the type of feedback. Okay, so in the main block we will have a non-ideal amplifier, and in the feedback we will have an ideal. The feedback or the box of the feedback will act as an ideal amplifier. And which type of ideal amplifier this will be, it will depend upon the input and output. Okay, so after connecting feedback, we will see the overall effect to this amplifier. For this amplifier there will be some gain, some input impedance and some output impedance. After connecting it, a feedback, there will be a overall system. So for overall system, we will connect gain with feedback, input impedance with feedback and output impedance with feedback. There will be 4 kinds of feedback. Okay, so for all those connections we will check the effect on these 3 quantities.